Hello everyone. Today I am Rishabh Bhardwaj, Assistant Professor from Mechanical Department, taking the lecture of heat transfer. Today in this lecture we will study about two-dimensional steady state heat conduction. Let's start with the introduction. The two-dimensional steady state with no heat generation is the Laplace equation can be applied, assuming that constant thermal conductivity is K, by which we can say that curl square of temperature with respect to the square of the x coordinate plus curl square of the temperature with respect to y square of y coordinates is equal to 0. Or it could be the z axis that could be nearly about to 0. Then the heat transfer in x and y direction may be calculated by the Fourier series, or it could be a Fourier equation that says that qx is equal to minus k a curl t by curl x, and for the y coordinate that will be the qy is equal to minus k a curl t by curl y. The total heat flow at any point in the material is resultant of qx and qy at any point. In the two dimension x and y, if heat is entering from the left hand side and goes upward to the outside, where T2 is smaller than the T1. For at any instant of the time, we are calculating the heat flow. Thus, the heat flow factor is directed so that it is perpendicular to the line of constant temperature in the material, as you have seen in the figure. So if the temperature distribution in the material is known, we may establish the heat flow. The solution to this equation may be obtained by analytical as well as the graphical technique or numerical technique. In contrast to the analytical method, which provide exact result at any point, the graphical and the numerical method can be provide only approximate result at discrete points. Let's start with the mathematical analysis of two-dimensional heat conduction. First, consider the rectangular plate as shown by the figure. Three sides of the plate are maintained at constant temperature T1, and the upper side has some temperature distribution impressed upon it, and that will be taken as the T2. This distribution could be simply a constant temperature or something from complex, such as the sine wave distribution. We shall consider both the cases. The temperature distribution for the coordinate x and y, but simplify the solution, we introduce the transformation, that in which the theta is equal to t minus t1 upon t2 minus t1, where from the three side t is equal to t1 and the total work done, that will be the t2 minus t1. From the equation, theta for the value or the coordinates of x and y is equal to 2 pi summation, where n is equal to 1 and goes up to the infinity, is minus 1, this is raised to the power n plus 1 by n into the sine n pi x by L into sine h into n pi y by L upon sine h n pi work upon length, where the L is the width of the plate, rectangular plate. The conduction shape factor and the dimensionless conduction. In general, finding analytical solution to the 2 and 3 dimensional heat equation is time consuming, and in many cases it is not possible. Therefore, a different approach is often and taken. For example, in many substance instance, two or more or three-dimensional conduction problem may rapidly solved by utilizing existing solution to be the heat diffusion equation. These solutions are reported in the terms of shape factor that is denoted by the S, or a steady state dimensionless conduction heat rate, that is the Q into SS. The shape factor is defined such that Q is equal to Sk change of temperature from process 1 to 2, where process 1 to 2 is the temperature difference between boundaries. Two-dimensional conduction resistance. That shape factor has to be obtained analytically for numerous 2 and 3 dimensional system, and results are summarized for the table, and the formula for that will be the resistance or the conduction for 2 dimension, that will be 1 by Sk. In this figure or the table, you can see the conduction shape factor and dimensionless conduction heat rate for selected system. The shape factor, that is Q is equal to Sk into change of temperature. For the case 1, the case 1 is isothermal sphere buried in a semi-infinite medium. In the schematic, you can see a cylinder circle by which it has to be bifurcated, and the center position is taken as distance from the center position to the upward, that will be taken as the Z, and it has D and the temperature T1, and the surface area, that is the surface temperature, that is the T2, where Z is greater than the D by 2, or D by 2 can be taken as a radius. Then the shape factor will be the 2 pi D by 1 minus D by 4Z. In the case 2, the horizontal isothermal cylinder of length L buried in a semi-infinite medium. In this figure, you can see that a cylindrical part with a length L and the diameter, that is D, is taken, in which the restriction are taken that L is more greater than diameter. Then the formula will implies that will be the 2 pi L by cos h inverse cos h by into 2Z by D. In the case that L by D, in the case Z is greater than 3D by 2, then the formula will imply that will be the 2 pi L upon natural log into 4Z by D. In case 3, the vertical cylindrical in a semi-infinite medium. In this, a complete cylinder are fixed below the surface, where it has been attached to the surface where temperature is T2. Here the length is L and the diameter is 2, where L is greater than diameter. Then 2 pi L, the formula that will be the 2 pi L upon natural log 4L by D. In the case 4, conduction between two cylinders of length L in infinite medium. in which we have taken a two cylinders. In two cylinders, the distance between two cylinders, that is W, and the diameter of the first cylinder is D1, and second cylinder diameter, that is a D2, and the temperature for first cylinder, that is T1, and the temperature for second cylinder, that is T2. Now the restriction has been taken that L is greater than D1 and D2, and simultaneously the L is greater than W. That W is the difference between the two cylinders. The formula that will be the 2 pi L by cos inverse H of 4W square minus D1 square minus D2 square by 2 T1 D2. The next, in case fifth, the horizontal circular cylinder of length L midway between the parallel planes of equal length and infinite width. In this, a cylinder has been taken between almost at the center and the between of two surfaces. That temperature will be T2, and the distance between the upper part and the lower part, that are also equal, that is Z. Here Z is greater than D by 2 and L is also greater than by Z. Then the formula that implies that will be the 2 pi L by natural log of 2Z by pi D. In case 6, circular cylinder of length L centered in a square solid of equal length, in which the restriction has been taken that W is greater than D and L is greater than W. The formula that has been taken that for will be the 2 pi L by natural log 1.08 W by D. In case 7, the eccentric center cylinder of length L in a cylinder of equal length. Here the restriction has been the D, capital D is greater than small d and L is greater than capital D. Then formula will be the 2 pi L by inverse of cos H into D square plus capital D square plus small d square minus 4Z square by 2 capital D into small d. In the case 8th, we have the conduction through edge of adjoining walls. In this, the condition has been taken that D is greater than 5L. The formula that will be the 0.54 D. In case 9, conduction through the corner of three walls with a temperature difference of process 1 to 2 or two bodies 1 to 2 across the wall. Here the L is smaller than the length of and width of the wall. In this case, the formula will be the 0.15 L. In case 10, disk of diameter D and the temperature T1 on the semi-infinite medium of thermal conductivity K and the temperature T2. Here the restriction has been neglected and the formula will be the 2T. In case 11, square channel of length L, where the restriction has been taken first that capital W, that is the width of outer surface, and the small w is the width of inner surface. Capital W by small w is smaller than 1.4, then the formula will be 2 pi L by 0.785 natural log of capital W by small w. If the capital W and small w is greater than 1.4, then 2 pi L by 0.930 natural log of capital W by small w minus 0.050 formula will be taken. In case 1 through 8 and case 11, two-dimensional conduction is pre-assumed to occur between the boundaries that are maintained at uniform temperature with temperature difference to T1 minus T2. In case 9, three-dimensional conduction exists in the corner region, while in case 10, conduction occurs between an isothermal disk T1 and a semi-infinite medium of uniform temperature T2 at location well removed from the disk. Shape factors may also be defined for one-dimensional geometries and from the disk. Case 12 to 15 are associated with conduction from sub-object held at an isothermal temperature T1 and that are embedded with an infinite medium of uniform temperature T2 at location removed from the object. From this infinite medium cases, uniform result may be obtained by defining a characteristic length. That implies the characteristic length will be the L is equal to AS by 4 pi under the root, where AS is the surface area of the object. Conduction heat transfer rate from the object to the infinite medium may then be reported in terms of dimensionless conduction heat rate. That will be the QSS steady state of shape factor is equal to the QLC by K by AS into the change of temperature from 1 to 2. The energy balance method. In many cases, it is desirable to develop the infinite difference equation by an alternative method from the energy balance method. This approach enables one to analyze many different phenomena such as problem involving multiple materials, embedded heat sources, and exposed surface that do not align with an axis of the coordinate system. In the energy balance method, the infinite difference equation for a node is obtained by applying conservation of energy to a control volume about the nodal region. Since the actual direction of the heat flow is often unknown, it is convenient to formulate the energy balance equation and assuming that all the heat flow into the node. That is the heat energy induced or generated that will completely become zero. Considering the applying equation to control volume about the interior node M and N, two-dimensional condition energy changes is influenced by the condition between M and N, and here is the four adjoining node as well as the generation. As you can see in the figure that here the value will be the M minus 1 N, in the center origin that will be the Mn, and above that is N plus 1, here M plus 1 in N and N minus 1, where width of the a column that will be the del X and the center to another position of the figure that will be the del Y, where I refer to the neighboring nodes and Qi is the origin Mn, is a condition rate between the nodes and the unit depth is assumed. To evaluate the condition rate term, we assume that conduction transfer occur exclusively through lanes that are oriented in the either the X or Y direction. If we simplify this in terms of Fourier, Therefore, it will be used for the as an example that the rate at which energy is transformed by conduction from node m-1n to mn will be expressed in the terms that k change of y to 1 into the t m-1 n minus t mn by del x, where the quantity del y into m is the rate of heat transfer area, and the term mn minus 1n and mn is the by x is the is the finite difference approximation to the temperature gradient at the boundary between the two nodes. The remaining conduction rate can be expressed in the three terms that are in the equation 3.4, 3.5 and 3.6. Substituting the equation from 3.6 into the energy balance equation 3.2 and remembering that the change of y is equal to the change of x is followed that the finite difference equation for the interior node will be generated as the equation that the term tmn plus 1 plus tmn minus 1 plus tm plus 1 n plus ttn minus 1 n plus q square of change of x by k minus 4 into t m minus m n is equal to 0. If there is no internal distribution source of energy, q is equal to 0. This expression will be the standard equation. Finite difference for convective or insulating surface. For example, the temperature may be unknown at insulated surface or at the surface that will be exposed to convective condition. For points on such surface, the infinite difference equation must be obtained by applying the energy balance equation. The node here we taken the example and the node represent the three quadrant shaded section and exchange energy by the convection with the adjoining mid at t infinity, and the conduction of the node region mn occur along four quadrant lane from the neighboring node in the solid. The conduction heat rate may be expressed in the terms of the formulas mentioned below here, that 3.9 equation 3.10 and 3.11 and 3.4 respectively. Note that the area of conduction from the nodal region m minus 1 n and m n plus 1 are proportional to the del y and del x respectively, where the condition from m plus 1 n and m minus 1 n occurs along lane of width del y by 2 and del x by 2 respectively. Conditions in the node region Mn are also influenced by the convective exchange with the fluid, and this exchange may be reviewed as occurring along half lane in the x and y direction. The total convection rate Q may be expressed in the term h del x by 2 into 1 t infinity minus t mn plus h del y by 2 into 1 and into t infinity minus t mn. In the absence of the transient and three-dimensional and generation effect, conservation of energy from the equation requires that the sum of equation from all the respective equations be 0. Assuming these equations and rearranging, we therefore obtain this equation, where t mn minus 1 n plus t mn plus 1 plus 1 by 2 t m plus 1 n plus t m n minus 1 plus h del x by k into t infinity minus 3 plus h del x by k into t mn is equal to 0, where again the mesh is such that del x is equal to del y. This is the summarized model infinite difference equation of dv is equal qv is equal to 0, where the q del x plus del x is equal to the del y. Here the for the different conditions that interior node and the node at the internal corner with convection and node at the plane surface with convection, equation has been written. And another we have the node at the axonal corner with convection and the node at the plane surface with a uniform heat flux. This is come to an end, and thank you for watching this video, and stay tuned for the next topics. Thank you.